My name is Seth, and I work at Northwestern University in Chicago, although I actually live here in Cambridge, so I work for them remotely. I've been programming in Scala full-time since 2008. I'll be talking today about the type class pattern, and my hope is that this should be at least reasonably accessible, even if you're relatively new to Scala. So feel free to interrupt even with what might seem like fairly basic questions about code and so forth. I'm going to start by explaining some concepts that are relevant to type classes. Then I'm going to go through an extended example with actual code where we'll be applying type classes to the problem of serialization. And then I'll close just talking about what's good about what we just saw and some cautions or downsides. Now, so this is the Scala Symposium. Why are we as Scala programmers in particular, why would we be interested in type classes? This is a word that doesn't necessarily come up when you first learn the language. The standard Scala book by Odersky, Venders, and Spoon, the word type class isn't even in the index or in the glossary. But my own sense is that particularly in the last couple of years that this is becoming a more and more common word that comes up in discourse around Scala. So this is something that you will probably want to know about in order to follow mailing lists and Twitter and some of the other talks today that will touch on this. The big software engineering concerns that this is about that aren't particular to Scala are polymorphism and decoupling. So I'll define different kinds of polymorphism in a moment, but to kind of sketch it broadly, we are, at the same time, we're trying to build our programs up. We're adding new types of data. We're adding new operations. We want those operations to work on these new kinds of values that we're adding. So we're kind of piling on. Our programs are getting bigger and more complex. So at the same time, we're trying to tear it back down, to tease it apart, and to keep our programs as being built from small independent pieces that can be independently understood and independently tested and so forth. So that's decoupling. The term polymorphism refers to when you can use the same operation and have it work on different types. And there's an old distinction dating back to the 60s between parametric and ad hoc polymorphism. With parametric polymorphism, the operation works on different types, but it ignores the difference between the types. So, for example, taking the length of a list. You want a length operation that works regardless of whether it's a list of int or a list of string or whatever. The difference doesn't matter. That's parametric polymorphism. Type classes address the problem of ad hoc polymorphism, where you want the operation to do something or potentially do something different for the different types of values that it accepts. Type classes originated in the Haskell language. They were included in the first Haskell standard in 1990. Haskell as a language was, the goal was to unify work that had been done previously in functional programming language design in languages like Miranda and standard ML, and kind of unify them into a single language that the functional programming community could kind of unite behind. So it mainly synthesized previous stuff, but it did break some new ground. And typeclasses in particular have been called the principal innovation that happened in Haskell. If you want to investigate the history more, this paper from 1989 by Wadler and Blott is the first real write-up of it. And we see them referring to ad hoc polymorphism in the title. Now, typeclasses come to us from Haskell. Haskell is a functional programming language. Is this a talk about functional programming? Yes and no, or actually really more no. Because when we talk about functional programming, we're thinking about the issues are immutability. We are using functions as values. And in pure functional programming, we are coding without side effects. Those are the big issues in FP. Typeclasses don't really touch on any of those issues, not in any major way. The issues instead, as I said, are decoupling and polymorphism. Now, nonetheless, there is some overlap with functional programming. This is important if you want to get more deeply into functional programming. For example, in the Scala Z library, which is the library that people doing pure functional programming in Scala use, almost everything in Scala Z is a type class. Monoids, monads, applicative functors, these are all defined as type classes in Scala Z. So I'm not really going to talk about that, but this is kind of foundational material if you were to investigate that. A brief note on terminology. In Haskell, type class is two words. So Haskell doesn't have any other kind of class. It's not an object-oriented language, so there's no confusion between on the word class or on the word instance. In Haskell, we also have instances of type classes. In Scala, which is object-oriented, we already have things called classes and instances. There's a danger of confusion. A type class is not a class. So Scala people usually write it as one word to help emphasize that. And in Haskell, this is a language feature. In Scala, it's just a pattern. It's not something it's not a word that appears in the language standard. It's just a particular combination of Scala language features, and I'll show you which ones are going to be relevant. So in Scala, we actually have a lot of different ways of achieving polymorphism already in the language. We can overload methods so that a method of the same name can accept different kinds of inputs. The really big one in object-oriented programming is inheritance. We get ad hoc polymorphism by overriding the behavior of a method in a subclass. And in Scala, we also have pattern matching, where we can look at a value at runtime and do something different depending on the outcome of this runtime test. I've marked those three with minus signs because we're not going to use those in the type class pattern at all. The language features for polymorphism that we are going to use, we're going to use traits or interfaces, as they're called in Java. And we are going to use type parameters, also known as generic types. So we'll see that in the code in a minute. The example that I'm about to start working through is about serialization. But you will see the type class pattern in other places. The two that you're most likely to see are in the Scala standard library. Numeric is a type class which allows you to abstract over different numeric types, to write code once and have it work on ints or longs or doubles and so on. And ordering is also a type class. That lets you specify when you're sorting data. You can specify how you want it ordered, and you can, the same type of value can be ordered in different ways at different times. Another really common example of when you would use this is for type-safe equality. The equality operator in Scala, which is mainly the same as the one in Java with only a few tweaks, it has this kind of pitfall, which is that it will let you compare values of any type. And if the types don't match, then you'll just get false. This is error prone because you may write code where you think you're comparing two values of the same type, but if you screw that up, the compiler isn't going to tell you. It'll just always return false at runtime. So if you want to look into it later, there's a link for a fairly small amount of code that will give you a type-safe equality operator. And as I mentioned, lots of type classes to be found in Scala Z. For this serialization example, we'll need a couple of domain classes. So these are just, person and restaurant are what we'll use. They've both just case classes with a couple of fields. Now, there are lots of different ways to serialize data. We could serialize to JSON, serialize to XML. We could do serialization the way the toString method does automatically for case classes. Lots of different ways for taking our data and reducing it to some sort of stream of characters or bytes. A first naive attempt at a serialized method that works on both of these types of data would be to just use overloading. But this really doesn't help us very much because with overloading, there's no connection between these two methods other than the fact that they happen to have the same name. Overloading, all it does is save you from having to choose new names all the time. But other than that, these are really two completely distinct methods. I can't call this method without knowing already which of the types that I'm using. So overloading is really not much help. But object orientation can help us. The standard OO way we would do this is to have is to use inheritance, so that in our person and restaurant classes we extend a superclass and then override the abstract method in each superclass. So this works fine. There is a small problem here, which is that we can only have one superclass. But that's easy to fix. In Java, we would use an interface. In Scala, we use a trait. And now we can say extends serializable with, and we can list other traits. So this now is the kind of standard object-oriented solution to this. And this is a perfectly fine solution. There's nothing. This is something that you're still often going to reach for, but it does have some disadvantages. In particular, we have a coupling problem here, where the person class, the information about how each of these classes is to be serialized, has to be actually in the class. Particularly if I'm wanting to support multiple types of serialization, or if I have lots of other operations, then my case classes, which used to be nice and simple, are going to get heavy with all of this stuff. And in order to add more traits and in order to add more overridden methods, I have to control these classes. These have to be mine. I have to be free to edit their source code and recompile them. Scala offers an alternative approach, which is to avoid inheritance and simply pattern match at runtime on the type. So I can, if I do it this way, I can leave the person and restaurant classes alone. They know nothing about how they're serialized. Instead, I have a serialized method that knows about each of the classes that I want to serialize and uses pattern matching to discriminate. And then if I want to do more than one kind of serialization, I can have more than one such method where with its own match, with its own list of cases. So we fixed the coupling problem that we had, but we've given ourselves a new coupling problem now, which is that these methods need to know about all of the particular classes that we want to be able to serialize. So I can't add new types of types to this unless this is my method. I control it. I can edit the source code and recompile it. Yeah. Eric has a somewhat longer, I think, talk about type classes that I'll link to later that presents an additional solution, which is to use reflection, and that has its own problems as well. So we're going to solve both of these coupling problems at once with this code, which is, we're almost at the type class pattern here. We're still going to refine it a little bit. I'm defining a trait called serializable. And what an instance of this trait represents is it represents the knowledge of how to serialize a particular type of value in a particular way. So the type parameter t is the type of value that we're serializing. So now, for example, here is how we represent the knowledge of how to serialize a person in this form, which resembles what the standard two-string method does. I put this in an object that extends the trait. I specify the type parameter, and I'm done. I can do the same thing with a restaurant. And now I can call this, but I have to supply this additional parameter to the serialize method that has the knowledge of how to serialize the particular class. So this is not so nice. We would prefer to have that be automatic. And we can do that by using the Scala language feature of implicit parameters. So this is the same code from the previous slide, but simply with the word implicit added. We've moved the serializable parameter to a separate parameter list, which is implicit. And when we declare this object that knows how to serialize a person, we declare it also as implicit. And that says this object is now available to be automatically filled in whenever we have an implicit parameter that with a matching type. And we've now achieved our goal. We can simply call serialize on a person. I only need to fill in the first parameter list. The compiler fills in the second parameter list for me. It runs, and this is type safe. If we pass a type of value to serialize that it doesn't, that the compiler doesn't have an available implicit for, then it will complain at compile time. we can refine this syntax a little bit if we like. Scala provides a shorthand where if you find yourself having to add these implicit parameter lists to many methods, you can shorten it like this by just putting a colon after the type and then saying what type of implicit you want to that you require for that type. So the example here is I have a method that will that knows how to serialize a list of any serializable type that we already know how to have, that we already have, and here's an example of using that on a list of people. Here the context-bound syntax is convenient because we don't actually need to use this value explicitly in the body of this function. So serialize here, there's an invisible second parameter list. The compiler is filling that in for us with this unnamed value. All of that code just sort of drops out. Another optional syntactic refinement that we can get if we want it is if we would prefer to write serialize as a method call on the object rather than as a function that takes the object as input. We can do that using an implicit conversion. This is the standard pattern for adding so-called extension methods to Scala classes. So I won't go over that in detail, but you have this option of making this syntax available to whoever's using your code. So that's the serialization example. And to recap, we have type safety. This is checked at compile time. We have two kinds of extensibility. We can add new types of data that are serializable. We can add new kinds of serialization like JSON or XML. And it's extensible in both of those directions in a decoupled way, where when we add when we sort of, you can imagine a matrix of like possible types of input, possible types of serialization. Every time we want to like fill in a box in that matrix, all we need is to add a new independent piece of code rather than altering existing code. Oh, yeah. So the question is, what if I wanted to serialize to something other than string? I did hard code string in this example, but you could imagine making that an additional type parameter to handle to do bytes instead or whatever. Yeah, you can imagine even more dimensions of variability for this. With what I've shown, this is even a little more flexible than what you have in Haskell because although normally it's convenient to have these implicit parameters filled in automatically by the compiler, you can also fill them in manually in case you need to override the default. For example, and this is using ordering, the ordering type class from the standard library. I might, in the same piece of code, want to sometimes sort person objects by their name and sometimes by their age. If I have implicits in scope for both of those kinds of sorting, then if I try to sort something, the compiler will tell me it's ambiguous. But I always have the option of filling in that implicit parameter list explicitly. So these two kinds of ordering don't need to step on each other's toes. The big difference, the really big difference between this and inheritance that you need to understand. The other solutions I presented using either inheritance or pattern matching, in both of those solutions, the decision of what code to run to do this serialization is happening at runtime. This is not true in the case of type classes. This will only work if the compiler has the knowledge at compile time to know which implicit to fill in. So that means that there are lots of, this is not a drop-in replacement for inheritance, because there are lots of kinds of code that you might, that you would expect to work with inheritance that won't work this way. For example, if I have a heterogeneous list containing more than one type of value, like a person and a restaurant in the same list, if I try to serialize that list, the compiler is going to complain, because the specific type information for the specific values in that list are lost when we stuff them into a list. I don't have time to get into detail about the various interactions with inheritance, but I do have links to a couple Stack Overflow questions that have good answers about what happens when both type classes and inheritance are in the same picture. So that's the big minus or difference, if you prefer, from inheritance. Some more minor downsides. The syntax is, there's a certain amount of boilerplate here. And when you see this boilerplate, it doesn't necessarily jump out at you that oh, this is the type class pattern. I mean, I see implicit here, implicit there. Like, what is this? Anytime you're using implicits for anything, there's a danger of obscure error messages. It's harder to call higher order functions. There is a kind of tax for using implicits of any kind. Tools like ScalaDoc and IDEs are kind of expecting normal methods. They're not expecting methods that are coming from type classes, so it can be harder to learn an API that uses this. And there may be some performance overhead. I'm adding extra layers of method calls. The resolution of the type classes does take place at compile time, so you don't pay for that. But there may be some performance penalty. Eric Osheim has been studying that in the context of the numeric type class. So that's if you are interested in numbers on that, you should look at his forthcoming Scala Days paper on the subject. There are some proposals out there for helping either with the performance or with the syntax or with both. The implicit classes and value classes proposals would both cut down on the penalty of extra objects being created. And Josh also has another proposal, which is like not, which is less on the fast track. You have to like write him to ask for it. But he has a proposal for making for reducing the amount of syntactic noise that using this pattern requires. So if you'd like to read more, there's a very short treatment of type classes in Josh's book with a different example, different from any of the ones that I mentioned. Eric's slides mostly go over the same material that I covered, but it's like a totally different presentation, so it might be interesting to get a different take on it. And that's all I've got. Thank you.